Hi everyone, I hope you guys are doing well. Welcome back to Padhai Logic. If you are preparing for your university exams and IoT feels like a massive tangled web of sensors, protocols and layers, don't worry. Today we are kicking off our IoT masterclass starting with the Unit 1, the foundation. So let's start by discussing the PYQ radar for our Unit 1. So very first thing we need to understand is that there is a question asked about IoT definition, vision, its characteristics and example. We'll talk about what are the technologies behind IoT and what are the sources. What are the three sources from which we are actually collecting data for IoT. We will also talk about M2M architectural domain, how it is different from IoT, what are the layers of architectural framework of IoT, and what is the conceptual model. So let's dig in. We will start with the absolute basics. What exactly is Internet of Things? So if you write in your exam that IoT is just connecting devices to the internet, you will miss out few items, right? So the formal definition is that IoT is a network of physical devices like vehicles, building devices and other items embedded with electronic software, sensor and network connectivity, which does what? It enables these objects to collect and exchange data. So in much simpler language, IoT is a global network of unique linked items, right? Uniquely addressable items which are communicating using digital communication, using digital standards, right? So there is a very magic word which is used in this. It is known as interoperability. Okay, interoperability. It is the main driver behind IoT's popularity. It means different devices from completely different manufacturers can talk to each other without a hitch. For example, imagine your traditional alarm clock. It only knows how to ring, right? But in an IoT ecosystem, your smart alarm clock talks to your coffee maker and your geyser. So the moment you hit snooze to your smart alarm clock, it tells the geyser, hey, give me 10 more minutes before heating the water. That's interoperability. I hope you mark this term, write this term, interoperability. This is a keyword and you need to use this in your definition, right? So now we'll talk about what is the vision of IoT. It is to design and develop an online and interactive platform where the objects will interact with other objects or persons remotely. So there are three visions of IoT, and at the intersection we have IoT. There are three visions: internet oriented vision, then we have things oriented vision, and then we have semantic oriented vision. So when experts look at IoT, they see it as a perfect intersection of three distinct vision, right? So first come up with internet oriented vision. This perspective focuses entirely on connectivity infrastructure. Okay, it is the idea that physical object can collaborate worldwide through standard internet protocols. Think of it as a highway system of IoT. To make this work, we need smart sensors for unique identification and microcomputers with real computational power to push that data over the web. Then we have things oriented vision. Here the spotlight shifts from the highway to the vehicles, right? To the things. So the vision emphasizes that the unique intelligence and capabilities that every single device bring to the network. This is what it is oriented towards, that is the things. It emphasizes on the importance of every individual device. So it is about turning dumb objects like regular light bulb into a smart object like bulb that tracks its own energy consumption and lifestyle pattern. right? And finally, we have semantic oriented vision. Now think about it. If millions of devices are constantly talking, they generate a mountain of raw data. How do we make sense of it? Who stores it? How do we search it? This is where semantics come in. Alright, this is where semantics come in. This vision uses smart data to frame and organize meaning to the data, ensuring that a huge influx of information actually becomes useful knowledge. Alright, so these are the three visions of IoT that plays a very vital role in discovering and defining how IoT plays and bring efficiency in the environment. Examiners love asking about architecture. So if they ask you for a basic view in 2 pointers, you can present them the 3-layered architecture. But if it is a bigger marker, you need to present the 5-layered architecture of IoT. So let's break down the 5-layer version so you can easily master both of them. So you see there are 5 layers to architecture of IoT. The very first layer at the bottom is the physical layer. So this is the foundation. Alright, this is the foundation layer. It consists of smart objects like sensors, actuators, and these sensors bridge the physical world and the digital world by capturing real world data like temperature, light, or motion. Next we have is the network layer. So once the sensor data is captured on the physical layer, it needs to travel, right? That is where network layer comes in. It provides a reliable wired or wireless network architecture using routers and gateway. So even though a machine to machine hardware has vastly different data requirement than human internet traffic, this layer ensures that the information reaches its destination, right? The very next layer is the middleware layer. So think of it as a brain and the manager of the system. This handles complex data processing, okay, and it performs security checks and device management as well. This is the middleware layer. So its secret weapon is the rule engine. This component helps automate tasks by running decision logic. For example, if rule engine says if temperature sensor data is greater than 40 degrees Celsius, trigger the cooling fan immediately. So it makes the entire system completely autonomous, right? The very next layer is the application layer. So this is the 4th layer. It directly provide interface with the user. So this is the mobile app on your phone or the web dashboard on your laptop. So it takes the raw numbers from the lower layers, run the analytics on them, and transform them into neat, meaningful insights that can be easily used. And on the top of every layer is the business layer. It manages the entire IoT system goal or business model, user privacy, and overarching deployment strategies. So basically it looks at a bigger picture of IoT. So before we move on, let's look at the classic conceptual framework equation of IoT. So if you write this formula exactly like this in your exam, you will immediately stand out. So the equation of IoT states that it is the addition of physical objects, controller, sensor plus actuators, and internet to create the entire Internet of Things, right? So now let's overlay into this Oracle 6-level procedural model. It is also known as conceptual framework, which explain exactly how data flow through an enterprise IoT solution step by step. So very first level is the level first. Here the data is generated. So the information is gathered right from the physical devices via sensors, right? So here data is generating or we are gathering it. Then comes the level 2. This is about transcoding, or we also known as a gateway. So data is enhanced. All right, data is enhanced, it is enriched and prepared at the gateway. So it might be encoded or decoded, so it is ready to send to the other party. Then comes the level 3, which is basically communication. The communication subsystem manages transmission and reception of the active data stream. Alright, so this is the third level. Then we have level 4, which is about device management. So the central device management system officially receives and validates the incoming data. Right. Then comes the level 5. This is about data repository. So the clean data is securely stored in an organized database or repository. Right. And then come the level 6, in which we are performing data analysis. Right. The system organizes, filters and analyze the data to deliver the final business value, what the action we would be taking. So this is the conceptual framework. You are asked to design the architecture of IoT, and giving an example, you can use this as well, right? So when you design a smart city, you structure it into 4 primary functional layers. First comes the physical layer, or it is also known as sensing layer. So the eyes and ears of the city is the sensing layer. Think of smart cameras tracking traffic, or parking sensors in the lots, or air quality monitors on street light, right? And then comes the network layer, which is the backbone. It uses city-wide network like fiber optics, 5G, LoRaWAN to transport data from thousands of street corners to a central control room. Then comes the middleware layer. It is where the data and platform comes together. So it is the centralized data platform which cleans, store and process incoming city data, making sure that a fire alarm alert takes priority over a routine trash can sensor whenever required. Alright, and then comes the application layer, where the interface, it is the interface for citizens and municipal staff. So this includes public transport tracking apps and smart city lighting control or emergency response dashboards and all of that. Then comes the business layer, who are playing a very vital role in making all this process efficient by providing insightful information to the businesses. Alright team, now we'll discuss about what are the technologies behind IoT. Think about it. How does a tiny moisture sensor buried deep in an agriculture farm talk to a cloud server thousands of miles away without draining its AA battery in 2 days? The answer lies in 2 critical areas, that is the communication protocols and the wireless transmission technologies. So let's break down the tech stack that you absolutely must sketch out for an protocol comparison question, right? So first we'll talk about communication protocols. These protocols are present in an application layer. First we'll talk about MQTT, which stands for messaging, queuing, telemetry, transport, right? So formally it's a lightweight publish subscribe protocol, network protocol. It was engineered specially for low bandwidth, right, high latency, and it is very suitable for unreliable network. So instead of client server system constantly pinging each other, MQTT relies on a central middleman called broker. So devices publish the data to a specific topic on the broker, and these devices subscribe to the topic to receive it. So what is happening in this, that there are multiple devices, right, and they are sending the data to a particular broker, and whichever device needs that data subscribe to that particular topic which is coming from this sensor. This is how MQTT works. So think of it as your favorite Instagram meme page. So the page owner is the broker. You don't constantly call the owner asking for new memes, right? You just hit the follow button. So the moment they post a new meme, the sensors publish, right? So it instantly appears on your feed. So it's incredibly efficient because your phone doesn't waste battery constantly refreshing an empty page. That is how MQTT works. Then comes CoAP, which stands for Constrained Application Protocol. So this one is designed for highly resource constrained devices. Think of a tiny microcontroller that only have a few kilobytes of RAM to spare. So unlike MQTT, CoAP runs on a request response interaction. So just like standard web browsing, but it is heavily optimized. It drops the heavy luggage of TCP protocol and runs on UDP protocol, meaning it shoots data packet fast without waiting for a complex handshake. It it is perfect for lower power automation environment where every millisecond of radio transmission costs precious battery life, right? And next we have HTTP. HTTP stands for Hypertext Transfer Protocol. So this is the old grandfather of web. This is the literal foundation of data communication on the World Wide Web. It is what your browser uses to fetch this video right now. Now you can see the use of it for IoT, right? It's widely used in traditional web pages, smart gateways, and powerful devices. But write this warning down that HTTP is heavyweight. It has massive header text file, meaning a tiny sensor trying to send a simple 1 or 0 has to wrap the data in a giant packet. So it will burn through a small battery in no time. So we use it when power isn't a problem, when like an IoT smart TV, because it is plugged directly into the wall, right? It has a power button always, so it can use the HTTP protocol with no worries. So these are the three types of communication protocols. Now let's move down to the hardware level. How do these things physically send data through airwaves? There is no single best wireless technology, to be honest. Instead, it is all about engineering trade-offs between range, speed, power consumption. So it depends. It varies on our need. So let's meet the 6 wireless technologies. First, we'll talk about Zigbee. So it is an open specification and it is built for low power efficient wireless technologies, right? So it is localized to provide localized control using mesh networking. So there are different types of network architecture. We talk about star, hybrid, mesh. I hope you know about this. So instead of every device trying to talk directly to a central router like we do in a star technology, that there is one central hub and other devices connected to it, Zigbee devices pass the data along through each other like a bucket brigade line. Okay, it is quick and it is incredibly cheap and it meets all the strict low battery efficient guidelines of the Zigbee Alliance, right? Next comes, okay, understand with a creative example. Imagine a massive smart mansion with 50 smart light bulbs. So the bulb in the backyard is too far from the main hub to connect, right? So with Zigbee, that backyard bulb simply hands its data to the kitchen bulb, which hands it to the living room bulb, which sends it to the hub. So no expensive range extenders are needed in such scenarios. That is why we use Zigbee. Next up is Thread. It is a relatively newer open standard. Okay, it is an open standard wireless protocol developed especially for modern smart home, and it is backed by a massive consortium of industry giants like Nest, like Apple, alright, and Google as well. So Thread operates on the exact 2.4 frequency band as Wi-Fi and Bluetooth, but it uses special underlying radio technology that is known as 6LoWPAN. So it is IPv6 over low power wireless personal area network. So it is using this personal area network, which is low power wireless. This means that every small thread device gets its very own secure unique IP address over the internet, making it highly scalable and secure without needing complex translation gates. Right? Now let's talk about Bluetooth. We already have it in our pocket. Bluetooth BLE stands for Bluetooth Low Energy. So because standard Bluetooth is a battery hog, engineers developed this BLE with extreme efficiency and economy in mind. Right? So you see, it keeps its radio completely asleep and only wakes up for a fraction of a second to burst small packets of data. So what is the trade-off? It's not meant for streaming large media files or high volumes of continuous data. Okay, so think of a smart fitness band. So it doesn't need to stream 4K movies, right? It just need to tell your smartphone app that heart rate is 72. So every few seconds. Okay, so BLE lets that fitness tracker run seamlessly on a tiny watch battery for weeks on end. Right, this is how BLE works. Moving out of the house and into a wider world, now we have NB IoT. This is a brilliant creation built right on top of existing 3GPP technology network, right? So the same towers your phone uses before, remember there were so long towers everywhere. So those cellular networks were replaced by this NB IoT. It uses narrow radio frequency band to provide exceptionally low power consumption. Even better, it offers incredible deep indoor signal penetration, handling signals that are approximately 23 dB lower than traditional 2G bands. So if your sensor is buried underground or locked deep inside the concrete basement, NB IoT is what you call. It is narrowband IoT, right? So if you want pure unmatched distance, look no further than LoRaWAN. LoRaWAN stands for Long Range Wide Area Network. So this is a low powered wide area network protocol designed to support network containing millions of devices simultaneously. So what it does, it sends tiny bursts of data over staggering distances like 10 to 20 kilometers away, while keeping power usage practically to zero. So imagine an industrial agriculture project covering thousands of acres of farmland. You can't put Wi-Fi routers in the middle of a cornfield, can you? So you plant a single LoRaWAN gateway at the farm headquarters, and the soil sensor mile away can transmit data flawlessly up to 10 years on a single internal cell battery. How amazing it is, right? Finally, we come to the king of familiarity, Wi-Fi. So Wi-Fi is based on historic standard, which is this IEEE 802.11 standard. We know it all and we love it for its blistering data speed up to 9.6 Gbps, right? But for industrial or battery constrained IoT, Wi-Fi has a major flaw. Okay, it has a major flaw. It has high power consumption. So it's hungry for energy. If you try to run an outdoor agriculture sensor on standard Wi-Fi, the battery will die in no matter of hours. Keeping Wi-Fi reserved for home hubs, indoor security cameras and devices that have permanent plug in the wall is completely alright, but it is not suitable for an agriculture project or wide area networks, right? So let's quickly have a look on this comparison matrix which you can completely draw down on your answer sheet to have a clear and concise view of how the technologies work in IoT. So if we talk about Wi-Fi, the range of Wi-Fi is 330 to 300 meters, right? And it is up to 9.6 Gbps data rate, and power consumption is very high. So it is mostly used in smart homes, IoTs, and healthcare. If we talk about Zigbee, it is widely ranging from 10 to 100 meters, and the data rate is 250 kbps. Power consumption is very low, and it is widely used for energy management, home automation. If we talk about Bluetooth or BLE, it is widely ranging from 1 to 100 meters only, and the power consumption is very low, up to 2 mbps, and it is used in wearables, smart locks, medical IoT. Then we have LoRaWAN, which is ranging from 10 to 20 kilometers, and the data rate is 0.3 to 50 kbps. Guys, when you design a smart device, you aren't just building a physical gadget, you are building an entryway to the internet. So examiners love to ask this 6-point checklist of what are the design principles for connected devices, and let's discuss that so that you can write down seamlessly. The very first is the user-centric design. So the principle number 1, the user need comfort and preferences that must be absolute center of your process. So the device must be intuitive, require zero painful setup, and offer dead simple instructions. So think of a smart bulb. If a user has to configure IP address to write command line just to turn on a living room light, it's a terrible design. A user-centric design means they plug it in, open an app, tap connect, and it works instantly. So the primary focus of the design process should be that it is intuitive, easy to use with minimal setup requirements. Then comes security. This is non-negotiable. Every connected device is a potential target for hackers. So a stellar design must bake security right into its DNA, including end-to-end data encryption, robust data authentication, and strict access control. So when imagine a smart door lock. Without encryption, the hacker could intercept the wireless signals and unlock your front door with a laptop. So security ensures that only your verified smartphone has the unique digital key to open that lock. Right? And then the third is interoperability, the highlight keyword, right? So your device should seamlessly communicate and collaborate with other devices and platforms completely regardless of who manufactured them or what underlying protocols they use. For example, if you buy a Samsung smart refrigerator and an Apple iPhone and a Xiaomi smart speaker, interoperability ensures that your iPhone can tell your speaker to look at the fridge status without any compatibility issues. Then comes scalability. So the architecture must be built to handle sudden massive tsunamis of data and especially scale up or down as more devices join the network without slowing down or crashing the system server. That is what scalability is. Comes to reliability. An IoT device needs to execute its job flawlessly across widely diverse environment, widely unpredictable weather, and fluctuating network connectivity. That is why it is very important for it to be reliable in any circumstances. For example, an agriculture sensor planted in a muddy field needs to withstand summer heat, needs to withstand heavy monsoon and patchy rural network signals, all while reporting accurate soil moisture data, right? So that is why it is very important for our IT connected devices to be reliable. Finally, we have power efficiency. Connected devices must be mathematically optimized to consume as little power as humanly possible to squeeze every last drop of life out of their internal batteries. For example, a smart pacemaker inside a human chest or a structural sensor buried deep inside a concrete bridge cannot be plugged into a wall outlet, right? It needs to optimize its sleep cycle so its battery can survive for a decade. That is what a vital role power efficiency plays in our connected devices. Data is the lifeblood of IoT. Without data, there is no smart decision making or automation. But where does it actually comes from? So in your exam, classify IoT data into three distinct buckets. First type of data source is the active data source. These are the sensors that are actively continuously sending the data into the network without needing to ask anyone. Alright, because they push data non-stop, the system must continuously extract, encode and store this live stream data for later analysis. For example, smart watches. They are tracking your real-time heart rate. For example, GPS location tracker on delivery trucks or temperature and humidity sensor inside a cold storage warehouse. They are constantly sending the data, right? Then the second type of source of data is the passive source. This is the exact opposite. Passive sensors do not broadcast data on their own. Instead, they simply sit down, quiet, and wait to be physically triggered or scanned by an external reader. So you can pull the data from them exactly when you need it, right? For example, RFID tags. So we'll talk about this in our next unit, what RFID is. So have you seen the tags on your retail clothings or your whatever item you're buying in a retail shop, right? Or you might have seen the NFC chips inside your tap to pay credit card or a standard barcode on grocery item. So they have no internal power source. They wake up when the scanner passes over them, right? Then there is the next source, that is dynamic source. By far it is the most advanced. These involve high-tech gadgets capable of having a fluid two-way communication with the central IoT software. This allows the system to change things on the fly. Like you can modify the data which is sent, right? You can alter the frequency of data, and you can also push the live data over the air, right? So for example, industrial machines on smart factory floor or AI powered real time city traffic monitoring system, they are dynamically adapt to their reporting interval during the rush hours. For example, during traffic hours, the sensors are reporting endlessly. But during the hours where there's no traffic, no such vehicle interference, the sensor is at that particular moment quiet, right? So this is how dynamic sources work. According to the requirements of the environment, they changes. The frequency is updated. Now let's look at machine to machine communication. Machines are creating data at unprecedented rate, right? When machine talk directly to another machine without needing any human intervention to streamline the operation, that is what M2M is, right? So M2M is widely used in asset tracking, in inventory management, in remote monitoring, and performance for devices, understanding the machinery, and using environmental sensor. So how does it actually work? So it follows a crisp, logical 5-step loop that you should illustrate if asked. Very first is data generation. So local sensors or machine automatically capture the raw physical data from their immediate surrounding, and then they transmit the data, raw data, over a local or private communication network using hardware standards like cellular, Bluetooth, Wi-Fi, and after the receiving machine or the local server intercepts the data, run pre-programmed rules and analyze it instantly. And then there is action. Based on the quick analysis, the receiving device make an autonomous decision and executes a command like triggering a safety valve or sounding an alarm, right? And after that we have the feedback phase. The final confirmation loop occurs where the system report back whether the automated action was successfully completed or not. So throughout this process we don't have any kind of intervention from human. All this is happening from machine to machine. If we talk about head-to-head comparison, think of M2M as a foundational stepping stone and IoT as a massive cloud connected universe that is built on top of M2M. So let's pull up a comparative matrix to memorize the incredibly simple concept of difference between IoT and M2M. So if we talk about IoT, it is a broad concept. It includes cloud-based application, it includes AI, automation, and it integrate analytics as well. So it has a massive ecosystem. But if we talk about M2M, it is a narrow scope. It is focused strictly on isolated device to device communication, nothing else. If we talk about network dependency, IoT requires internet and cloud or cloud apps. It requires a cloud for remote control and massive data storage as well, right? But for M2M, it can fully run offline using local or private networks without any internet requirement. For data processing, IoT data is scaled up and processed via cloud platform. Okay, but in M2M, data is processed locally on a centralized server, which is a legacy server presented in the organization for decades, right? Then we have a communication type. In IoT, there are multi-directional communication. There can be machine to machine type of communication, machine to cloud, human to machine. There are various types. But in M2M, it is strictly point to point, machine to machine only, right? There is no other intervention. Then there, if we talk about complexity, it is highly complex to maintain and set up an IoT infrastructure. But if we talk about M2M, it is simpler and it often is just using sensors and local network, that's it. And IoT is highly scalable. It supports millions of devices, whereas in M2M there is limited scalability. It is mainly used for only specific applications. Up until now, we have learned how devices talk and what networks they use. But once those millions of sensors start blasting raw data to our system, we face a massive bottleneck. A raw data on its own is pretty dumb. If a sensor spits out a number, for example 38, what does that even mean? Is the sensor sending us 38 degrees Celsius? Is it the device ID or is it a high risk anomaly? So to make the raw data usable for business decision, we need to master two massive topics, that is data enrichment and consolidation. So let's break down these concepts step by step. Data enrichment is the process of enhancing raw data that is collected from IoT devices with additional context, right? With additional context, metadata, or external or relevant information to add the value and depth to the data. So you are essentially taking pre-existing first party data set, alright, and combining them with the third party data sources. Think of it like a raw IoT data is just a bare skeleton. Data enrichment is putting clothes, muscles, and a brain onto the skeleton so it makes a perfect sense to the application layer, right? So that is the work of data enrichment. There are three types of data enrichment. First is time-based enrichment. So adding precise timestamps to the raw data. This helps us track the historical trends. This is to track the time series interval, that what was happening at what particular time, and the exact sequence, exact pattern, right? Next we have location-based enrichment. This is about injecting geographical context, like GPS coordinates are added to the data, postal codes or country markers to map out exactly where the transmission was originated. Then we have device based enrichment, in which we are attaching critical device metadata like the unique hardware ID, firmware version or manufacturer specifications. If we talk about what are the methods we use for data enrichment, for example, data fusion. This is the technical process of integrating multiple distinct data sources to produce information that is more consistent and accurate than any single source. For example, we are merging a local tractor's ground level temperature sensor data with an overhead weather satellite feed. So this is the data fusion. So it might means combining the data set to provide a meaningful, useful information. Then comes data normalization. This is about adjusting data points measured on completely different scale onto a mathematically common scale. Okay, we are normalizing the data. For example, if a sensor A in Germany sends temperature in Celsius and sensor B from US, it sends it in Fahrenheit, right? So these are completely in different formats. Data normalization translate both into a uniform scale so that the system can compare them accurately. Then we have data aggregation. Data aggregation means gathering massive stream of raw data, repeating telemetry or expressing it in a summarized format for statistical analysis. So instead of overwhelming our database by storing every single tiny set sent by the sensor every millisecond, what we do, we aggregate the data and store just an hourly average, that what was the average of a sensor by hour, by storing milliseconds, and then we'll have millions and billions of row of data, and it would be very hard to perform analysis on that. That is why somewhere we do require to aggregate the data. And then we have entity extraction. This means automatically identifying, isolating or indexing the key subjects within an unformatted data stream, such as extracting specific device profile or user account layer to build a structural profile. So these are the few methods which are used in data enrichment. If we talk about some use cases, that where is exactly the data enrichment is used. First we'll talk about smart agriculture. So a raw soil sensor reads 15% moisture and the system enrich it with a third party weather forecast showing a 90% chance of rain in an hour. So the system decide not to turn on the irrigation pump. So this will save us thousands of liters of water. That is why we use data enrichment. So the data source is coming from different types, right? One is coming from sensor, one we are having third party weather forecast. Combining them, we are taking the decision. System decides that not to turn on the irrigation pump. Same we have for fleet management. For example, a cargo truck's raw GPS coordinates are constantly enriched with live traffic congestion map, right, and the real-time fuel price data to change its routes on the fly and save the shipping cost. That is how data enrichment plays a very vital role in performing efficient tasks, right? If we move forward, we have a massive trap for students when there is asked a question, what is the difference between data cleaning and data enrichment? So let's clear up this trap. First, data cleaning is about removing the noise, removing errors, or if there is any anomalies in the data. But data enrichment is about adding the value, adding context and intelligence to the data. In data cleaning, we perform the actions like deleting, correcting, or duplicating data entries. Whereas in data enrichment, we are supplementing and enhancing the data. Right? We are expanding the data fields. Core focus of data cleaning is to maintain internal consistency. Whereas in data enrichment, increasing the external depth of the data is our core focus. If we talk about the analogy which is used in both the concepts, data cleaning is about erasing the mistakes, right? It is about erasing mistakes out of a student notebook. That is what cleaning data is an example. But data enrichment would be like adding the research notes directly into the margins of our report. That is what data enrichment is. I hope the difference between both the terms are clear to you guys. While data enrichment adds extreme depth, data consolidation is a structural glue. Okay, so write this down. Data consolidation is a process of combining data from multiple scattered sources into a single, centralized, and unified review. Remember how we established that IoT has massive data volume problem? So consolidation is the cure. While data enrichment adds extreme depth, data consolidation is the structural glue. Okay, so data consolidation is the process of combining data from multiple sources, multiple scattered sources into a single unified view. So remember how we established that IoT has a massive data volume problem? Consolidation is the cure. It brings data out of isolated silos like combining company HR records, real-time sensor streams, and external matrices to ensure complete data integrity, to ensure that there are no duplicates and there is absolute storage efficiency. That means reducing the database bloating. So to achieve data consolidation, almost all enterprise IoT architecture relies heavily on classic ETL framework. We have discussed in detail about ETL framework in data warehouse and data mining videos. Please go and watch that if you want to have a detailed understanding of how ETL works. So extract, we are gathering the raw data, safely gathering them from the edge devices, from the distributed cloud databases and various external APIs, and then reformatting the data into a single corporate standard. This is where we clean out all the ghost readings from broken sensors and also filter out whatever useless pings we have and run deduplication algorithm to ensure that the same repeated wireless signal isn't counted twice. Then we load the data. Safely inject the finalized hyper clean consolidated data into a central repository like data warehouse or data lake. Right? So the core objective of data consolidation is to provide a unified view, is to bring data together, integrate it, ensure there is no duplicate, and provide storage efficiency. And that, my friend, conclude unit 1, the foundations of IoT. We have covered everything from definition, the visions, 5-layer architecture, wireless protocols, M2M mechanics, and all the way to data enrichment workflow. Now you are looking at the PYQ radar we have discussed initially, right? So I want every single one of you watching this right now to pause the video, take out a blank piece of paper and try answering this question under exam conditions. Try just writing high yield keywords which you have learned in this particular video. Alright, thank you so much for tuning into Padhai Logic Unit 1. If this video helped you clear up the fog around IoT Foundation, make sure to slam that like button, subscribe to the channel and share this playlist so that everyone can ace their exam together.